Hello everyone. Today I, Aakanksha Tewari, am going to present our topic, Reconfigurable Wireless Wi-Fi with Dynamically Controlled Out-of-Band Emission and its Design and Performance Analysis on Zynq SoC. Orthogonal frequency division multiplexing is widely preferred for 5G wireless and next generation Wi-Fi due to its low complexity, simple receiver and compatibility with legacy system. However, one of the well-known drawbacks of OFDM is its high out-of-band emission. High out-of-band emission leads to poor spectrum utilization due to the guard band requirements between users on adjacent carrier frequencies. In our work, we aim to address this challenge by augmenting OFDM PHY with low complexity time domain windowing and frequency domain filtering operations. By using the dynamic partial reconfiguration property of Zynq SoC, we aim to demonstrate the dynamic switching between simple OFDM waveform, window overlap and app-based OFDM waveform, and filtered OFDM waveform, and also between the different filter orders and window types. For our system model, we have considered the N78 frequency band in frequency range 1 and 4096 subcarriers per OFDM symbol. In our proposed block design, we are using the transport block to generate the bits which are to be transmitted. They pass through the channel encoder and then through the data modulator. The resource mapping block maps these so the data demodulator converts them to complex symbols and the resource mapping block maps these complex symbols to subcarriers. This is followed by OFDM modulation, which comprises of 4096 IFFT and CP addition and either windowing or filtering blocks. So in our design, we have considered 4 windows: Han, Gaussian, Hamming, and rectangular window. And we have considered 4 filter orders, which is 64, 128, 256, and 512. These symbols are then passed through the wireless channel, which we have modeled as an AWGN channel. And on the receiver side, the same operation take place in reverse order, that is windowing or filtering, followed by CP removal and 4096 FFT, followed by data demodulation, and then channel decoding. And the received bits are compared with the transmitted bits to find out the bit error rate. Our proposed reconfigurable architecture on Zynq SoC is made via the hardware-software co-design approach, where some of the blocks are implemented in PS and the other blocks are implemented in PL. The complex symbols from the output of the MCS block in PS is sent to the OFDM transmitter in PL via the transmit DMA. Resource mapping, 4096 IFFT, and CP addition blocks comprise of the static region in the PL, and the reconfigurable region comprises of 2 DPR blocks, one of them in the transmitter and the other one in the receiver. Depending upon the 5 parameters and the waveform selected by the user, these blocks can be appropriately configured with the respective partial bit stream. So they can either implement a window functionality or filter functionality, depending upon the user requirement. After windowing and filtering, the complex symbols are sent back to the PS and they are passed through the AWGN channel. Depending upon the SNR entered by the user, the respective noise is added to the symbols and then they are sent back to the PL to the OFDM receiver. From the receiver, they are again received and sent to the PS, where the performance analysis takes place and the results are displayed using the display unit. In our design, we have implemented DPR using 2 approaches. The first one is through the processor configuration access port, and the second one is through our custom IP Zynq, which uses the internal configuration access port to perform DPR. This table compares the reconfiguration time of both the DPR approaches for the 2 reconfiguration region. And we can see that with Zynq, we are able to achieve a much faster reconfiguration time as compared to PCAP, which is up to 3 times more faster. Now coming to the experimental results, we have demonstrated them in terms of PSD and bit error rate plots. This figure, it compares the PSD of the OFDM waveform with the VOLA OFDM waveform for 3 different windows. We can see the VOLA OFDM waveform gives us much lower out-of-band emission as compared to simple OFDM, up to 30 to 80 decibel watts per hertz lower, and thus gives us a better PSD plot. Here we can see that FOFDM gives an even lower out-of-band emission as compared to VOLA OFDM. In this figure, we compare the PSD plots for different word lengths for the 3 waveforms. We see that as the word length is decreased, the out-of-band emissions also deteriorate. As in the first plot with 32-bit word length, we can distinctly see the out-of-band emissions of the 3 waveforms. The second plot, we can see that FOFDM and VOLA OFDM, the out-of-band emissions are overlapping. And in the third, we can see that for all the 3 waveforms, it is overlapping, which corresponds to a 16-bit word length. In the for the bit error rate plots, we have also demonstrated for different waveforms. This black plot is for VOLA OFDM. Since all windows were giving an identical plot, we have only kept one. This is the variation of the bit error rate with increasing order. As the filter order increases, the bit error rate reduces. And also on comparing QPSK and 64 QAM modulation scheme, we can see that the QPSK modulation scheme gives much better immunity to AWG and noise as compared to 64 QAM. The second plot is comparison of word length for different waveform. So we can see that as the word length is increased, the bit error rate decreases for all the waveforms. Now, we analyze the complexity of a design in terms of resource utilization and power consumption for different architectures. Considering the OFDM architecture, simple OFDM, we see that it has the least resource utilization and power consumption. Architectures 2 and 3 are reconfigurable and non-reconfigurable architectures containing OFDM and VOLA OFDM waveforms. VOLA OFDM is demonstrated with 4 types of windows. So we can see that in the non-reconfigurable architecture, the VRAM utilization is much higher since these windows are implemented in parallel and they require more on-chip memory for storing the window coefficients. Similarly, the reconfigurable architecture has more LED and flip-flops requirement to implement the DPR functionality. Also, the non-reconfigurable architecture, if we wish to increase the number of windows, again, the VRAM utilization will have to be increased. Whereas for the reconfigurable architecture, it is independent of the number of windows which we want to keep in the design. Similar observation can be made for architectures 4 and 5, where we are using OFDM and FOFDM together. For architecture 6 and 7, so we have all the 3 waveforms integrated here, the reconfigurable and non-reconfigurable architecture. The resource utilization of non-reconfigurable architecture is much higher than the reconfigurable one. Also, the power consumption is much higher, thus demonstrating that our reconfigurable architecture outperforms the non-reconfigurable architecture. In this table, we compared the word lengths of the architecture 6 and 7 for word length 32 and 24 bits. And we see that with increase in word length, the resource utilization also increases. So we can observe that if you want to increase the word length, the out-of-band emissions and the bit error rate decreases, but it decreases at the cost of increase in resource utilization, dynamic power, and also increase in latency. We also wish to increase our, extend our proposed work to an intelligent reconfigurable architecture by adding intelligence so that our PHY can sense the radio environment and accordingly choose the PHY parameters. Now I'm going to demonstrate the demo. So here we can select the modulation type, waveform, window type, filter order, and word length, and correspondingly the respective bit stream is run and the results are displayed. So here I have selected OFDM with 64 QAM modulation and for 32 bits. This is the constellation diagram corresponding to 30 dB. Once I start it again, the SNR will start varying from 0 to 30 dB. And the corresponding constellation and bit error rate plots would be displayed. As you can see, this plot corresponds to 0 dB SNR. SNR will keep increasing till 30 dB. The red dots here correspond to complex symbols before data demodulation. And these symbols are scattered across the constellation plot. And as SNR increases, they would approach the golden complex symbols. Thank you.